Hello, how we doing? Back for more. Hello, my 16 people. Oh, it's going up. How we doing, Mary, Lyric? Good to see you guys again. You've come back for more. Obviously, I didn't put you off yesterday, which is great. That's a great start. We are going to start doing some recapping. All right. So today, it seems an almost impossible task to cover rates of reaction and everything we need to know about that: orders, deducing orders, the rate equation, the Arrhenius equation, maybe even some rate determining steps if we get time. So we're going to crack on. Okay, guys. So hello to you all. And thank you for coming along. I mean, it's really good to know that we have got a good uptake on this. It's really pleasing to know that you guys are joining us. Okay. So rates of reaction, ladies and gentlemen, let's just get started, shall we? So let me just share my iPad and get my pencil. Okay, so you should all be seeing my iPad just about now, coming up, blank screen. So hello, who's new in here? Who wasn't here yesterday? Who's just found us today? So we're looking to try and reach as many students as possible. Okay, recapping, just making sure you're staying in touch with your studies. Obviously, a really sucky situation, as obviously with the exams and stuff like that. So great. Oh, loads of new people in here today. That's absolutely amazing. Okay, so what we're going to try and do is just kind of, I don't know, iron out the creases, maybe get rid of some misconceptions you've got about rates of reaction. And that's what we're doing. We're just having a recap session, okay? Anush, you've been hard at it since 11 today. That's amazing. That's great. So loads of really new people in here, which is absolutely amazing. Okay, we want to try and reach as many students as possible, keep you excited about your studies. Okay, maintain that motivation for your studies and just keep you in touch. And yeah, so that's great. Absolutely great. So rates of reaction, ladies and gentlemen. First things first, what we need to know is from year one, we need to know our basically collision or particle theory. Okay, so I'm going to assume that you all know like how to explain why increasing temperature increases a rate of reaction, why increasing pressure, or why increasing concentration or surface area and all those things. You should be able to explain that. That's year one stuff. Okay, we're not here to do that. Neither are we here to look at Maxwell-Boltzmann's and things. We are looking at the rate equation. Okay, now of course our rate equation says this. So if you've got two reactants and you're forming two products, okay, what we need to do is we know that if we increase the concentration of A, it should increase the rate of reaction. The same for B. We know that if they're gases and we increase the pressure, that's kind of like increasing concentration, forcing the particles closer together, and that increases rate of reaction. It's all about collisions and successful collisions at that, okay? So we need to take that into account. Now, we told you a little bit of a porcupine in year one is that we increase the concentration of anything and it increases the rate of reaction. That's not true. Okay, that's not true. You can increase the concentration of some reactants and it does naff all with respect to the rate of the reaction. And we discover this in year two and we start to quantify this in year two. Because in year one, like kinetics and equilibrium stuff, it's all like, oh, it shifts to the right, it shifts to the left, or oh, it increases concentration, increases rate, or it decreases rate. It's all very qualitative. It's kind of like, yeah, but by how much? Okay, so what we're doing in year two is building on our knowledge from year one and quantifying it. And that is what the rate equation is all about. So our rate equation is this: rate equals the rate constant K multiplied by the concentration of any reactants that actually take part, that actually have an effect on the rate of reaction. Okay, but only those that actually have an actual impact on the rate of reaction. Now, of course, what we can do is look at how there are three ways in which a reactant can actually affect the rate of the reaction. Okay, so if we increase concentration here, and this is rate. So we have got three lines to consider: this one, and this one. Okay, so what's this one here? Let's call this 1, 2, and 3. Let's put the 1 over here just to make it clear. Okay, so 1, what does that tell us? Well, that tells us that if we increase concentration of that particular reactant and it has no effect on rate, boom, it's 0 order. So 1 equals 0 order. So no effect. You can put as much as you like of that in. It's not going to affect the rate of reaction. 2 is obviously first order, and I can see people already writing that in the chat, which is amazing. And then 3 equals second order. Okay, so this is no effect on the rate of reaction. This one is, what word would we use to describe that first order? What word would we use to describe that relationship? Oh, I think Jazz has already written it. Yeah, double concentration doubles the rate. So they are proportional. Okay, this is proportional. So if you double it, the rate's going to double. If you triple it, the rate's going to triple. Or if you increase it by a factor of 4.72, the rate's going to increase by a factor of 4.72. Now, second order, what word would we use to describe that? So the relationship between increasing the concentration and the effect it has on rate. So what word do we use to describe that? Is there such a thing as third order? Yeah, I think it's probably more exponential. Yeah, absolutely. Exponential is the word. So basically, if you increase concentration by 2, the rate goes up by a factor of 2 squared. Okay, so that's where the second order comes from, because it goes up by 2 squared. There is such a thing as third order, whereby it's not in the spec, FYI, but it would go up by, however, if you double the rate, it'll go up by 2 cubed. Okay, so it has a really big impact on the rate of reaction. Okay, so it's proportional to the power of X. Absolutely, yeah. So we only have to deal with these 3 at A level. Okay. Now, when it comes to our rate equation, of course, let's say we know that this is first order and B is second order. To write the rate equation for this, you lift the powers of the order onto those concentrations. So this would be a to the power 1. So you wouldn't write anything there, because anything to the power 1 is itself. And then this would be squared. So our rate equation for this would be K times concentration of A times the concentration of B squared. Okay, perfect. Absolutely perfect. So obviously, a lot of questions given some data would ask you to find the value of K. Okay, so all we need to do is rearrange this. So what I do to rearrange, because I'm not a great mathematician, I'll hold my hands up. I always say this because it's true. It's rate equals K times A times B squared. Okay, so all we need to do to rearrange it to find K is take these, okay, and put them underneath rate. So K equals rate divided by the concentration of A times the concentration of B squared. Okay, so it's all you need to do to rearrange. That is by far the most common rearrangement that you guys have to know to answer any questions. All right. So that's how we find K. The units of K are really, really important. So if we're looking at units, rate is usually moles per decimeter cubed per second. All right. To find the units, it would be moles per decimeter cubed, because that's it for A, times moles per decimeter cubed times moles per decimeter cubed. And I've put 3 of those in because 2 of them come from this bit squared. It's like moles per decimeter cubed times moles per decimeter cubed, isn't it? Okay, so that's why I've done that there. So to get the units, all we have to do is cancel. So we end up with cancelling that. We're keeping the per second and cancelling that. So those 2 cancel out. So we end up with S minus 1 over, now this is moles squared, decimeter minus 6. So how would we turn that into our overall units, guys? Oh, Lyric, that's equilibria. Let's not go down KP road, okay? Square brackets for concentration, this is true. Boom, Jazz, absolutely. So because we bring these up to the top, we invert our powers. So we end up with moles minus 2, decimeter 6, S minus 1. Okay. Now, some exam boards don't need to do that. I just thought it was important. AQA, you definitely do. Okay. You can put these either way around. You should technically put the DM6 first, but they're never, ever going to mark you down for writing it the way I've done just there. Okay. Which is really, really important. So, obviously, this rate equation, it's all based around concentration. It's all based around concentration. I just want to point something out to you. All right, let's just get rid of this rubbish over here. Okay, let's go see if we can get rid of that. Okay, see if we can get, no, I want to get rid of that little cross. There we go. How do we, what factor, okay, K doesn't change for a reaction unless you do what? What's the only factor that can actually affect the value of K for a reaction? Good, Raseb. Temperature. Temperature is the only thing, okay? Temperature is the only thing. Now, how does this rate equation tell us that, okay? And I want to be really, really clear here. How does this rate equation tell us that? Well, it's because we know that temperature affects rate. Temperature doesn't affect concentrations, okay? You can increase or decrease the temperature of A and B all you want. It's not going to change their concentrations, but it does affect the rate. So, of course, if it does affect the rate, the only other factor, because, of course, this is still true, absolutely true. So if I increase the temperature, I increase rate. Well, if it doesn't affect these, what must temperature affect the value of if it doesn't affect the concentrations and it is changing the final value of rate? What must it be affecting the value of? K, absolutely. It must be affecting the value of K. So what we can say is that if we increase temperature, K must also increase because rate is increasing. So this must be increased as well by increasing the temperature. Okay. Now bear that in mind when we get to the Arrhenius equation in a minute. Okay. Why don't K affect concentration? Well, K and concentrations they're separate factors. K is just a constant. Okay, it's not a condition. It's not like temperature or pressure or anything like that. K is just a constant. Okay, why doesn't concentration affect K? How can I put it? When we look at the Arrhenius equation, you'll understand. Okay, let's just keep it at that. Okay, so temperature must affect K because that's the only way, looking at our rate equation, that it can affect rate. Okay, it's the only in we've got. Okay. Why does temperature not affect concentration? Well, it doesn't. You've still got the same volume. You've still got the same number of moles. Changing the temperature doesn't affect the number of moles you have and doesn't affect the volume that you have. Okay, so it may affect it slightly, okay, by things expanding. The liquid may expand a little bit, but you know, we're not taking that into account. Okay, temperature also affects Kc and Kp too. Yeah, good shout. Okay, so whenever you see K, whether it's equilibria or rate, the only thing that can change it is temperature. Okay, so whether it's K in the rate equation, Kc, or Kp, it doesn't matter. The only thing that can affect that value is temperature. Okay, boom. So onwards and upwards, we do need to move on. I've got a question for you, ladies and gentlemen. So knowing orders and knowing this, let's just see if we can work through this together. This is a template note from our course, from my course. So we need to, this is a typical presentation of data that you might find in an exam paper. Okay. Catalyst doesn't affect K either, or will it? Yes, it will affect K also. Okay, purely because, again, trust me, when we get to the Arrhenius equation, we'll work it out. Okay, so what we've got here is typical data that we've got. We've got a number of different experiments over here on the left, and we've got initial concentrations of A, B, and C, and the initial rate on the right-hand side as well. Okay. Yeah, so let me just talk you through this, okay? So I'm not going to pay any attention to the chat just for a minute. I'm just going to talk you through it. So if they ask you to find the order of reaction, I'll tell you what, they're asking you to write the rate equation for this. So what's the rate equation for this? Okay, that's the question. So we need to know the orders, first of all, or maybe they're asking you to find K, all right? So the first thing I'll do is look at all these runs. Now, what I'm going to do is look for one of these, okay, for A, B, or C, and I'm going to look for two experiments whereby the concentration of one is changed and the other two remain constant. Okay, it's really important. Think of it like fair testing when you were doing GCSE, right? Oh, you only change one variable at a time. That's all we're doing here. All right. So have we got it for A? Well, we've got 2 to 1 here, but that changes, and that changes, and that doesn't change, but we can't do that. 2 to 1, no. So we can't do it for A, but we can do it for B, I think. So we get 0 point, yeah, here. So notice how this changes, 0.1 to 0.4, whereas this stays the same and this stays the same. So we can do it for B first. And once you've got one, you've gone into the others, okay? So we're not revising, Muna. We are making sure that we stay in touch with our studies, because who knows, well, you'll either be doing an exam in September if you're not happy with the grade you get given, or you'll be tested when you get to university. So finding B. So it goes, so the concentration between experiments 1 and 2, I always write that. Concentration of B has gone up by a factor of 4. It's gone from 0.1 to 0.4, okay? Now, what's happened to our rate? The easiest way to do this is just divide one by the other. So I'm going to do 3.2 times 10 to the minus 3 divided by 0.8 times 10 to the minus 3. And that means rate has also gone up by a factor of 4. Let me just show you that on the calculator. Okay, I'm really tiny right now, but that's a 4 on my calculator. Okay, so therefore it's first order. Good. Okay, so B is first order. All right. Now, how do we find the rest of it? Well, we know that B is first order, so we can now account for that. See this here? Like so. Okay, so for changing the concentration of A, this has gone down by 0.1. It's gone down, it's been divided by 2. This has stayed the same, so we can ignore C, but B has also doubled. Okay, so what we think here is, so for finding A, that the concentration of A has been divided by 2. Okay, it's gone down by half. Now, C we can ignore, but B has gone up by 2. Now, we know that B is first order. Okay, we know that B is first order. So this is what I'm going to do. I'm going to take this, okay, and I'm going to multiply it by 2 to account for B. I'm going to account for B first because B's been doubled. We know it's first order. So if it's going from 3.2 times 10 to the minus 3, now, if we just had B in the mix and we doubled B, it would become 6.4 times 10 to the minus 3. So if we just take B into account, we get 6.4 times 10 to the minus 3. But of course, that's not that, is it? It's actually 1.6. So what has happened to the rate, okay, taking A into account as well? So if you just take B into account, it should have doubled, but it hasn't. So I've accounted for that and multiplied 3.2 times 10 to the 3 by 2. And then what I'm going to do is find out what the difference is between 6.4 times 10 to the minus 3, which is what it would have been if B has been doubled, which it has, and 1.6. So I'm going to divide that by 1.6 times 10 to the minus 3, and that gives me 4. Okay, so 6.4 down to 1.6 times 10 to the minus 3. That's basically divided by 4. And that is the effect that A has. So if A's been divided by 2 and the rate has gone down by a factor of 4 or 2 squared, that means it's second order. Good. And I'm sure some of you had already written that in the chat by the time I'd explained, but I'm trying to explain it for everybody. Now, lastly, C, we need to look at how we get C. So I would say that I'm not going to use this bottom one here because it looks a bit sucky. I'm going to go, well, we have to use the bottom one. Yeah, we have to use the bottom one. I'm going to use the top one and the bottom one, experiments 1 and 4. Okay, so 1 and 4 I'm using. So we start with 0.8 times 10 to the minus 3. Now A has been halved. So 0.8 times 10 to the minus 3 divided by 4. Because A's been halved, we know it's second order, it's gone down by 4. That gives me 2 times 10 to the minus 4. C has also been halved. Okay, so I'm going to divide that by 2 again, because we know that's first order. Hang on. No, B. Let me start again. 0.8 times 10 to the minus 3 divided by 4. That gives me 2 times 10 to the minus 4. We want to find C, don't we? B's been increased by a factor of 3, and that's first order. So I'm going to times that by 3, and that gives me 6 times 10 to the minus 4. And C has been halved, okay? Now, what's the difference between 6 times 10 to the minus 4 and 0.6 times 10 to the minus 3? Nothing. C's had no effect. So all I did, just to recap, was I took this number here, I divided it by 4 to account for A. And then what I did is I divided it by 2 again to account for C. And that's basically given me that number. Now, taking into account the fact that initial concentration of B has been tripled, well, I've already got that number. So obviously changing B has no overall effect. So changing C. So a 0 order for C. Okay, so C's been halved. There's been no change in no change in rate. So that's why I do that. Okay, so it's 0 order. Absolutely lyric. Yeah, that's it. Okay, so why does the rate account for A and C? So essentially, I take 0.8 times 10 to the minus 3. I account for A. So I divide it by 4, which gives me 2 times 10 to the minus 4. Okay, so I've accounted for A. A would have had that effect on that initial rate, right? So then I took into account B and multiplied that by 3, which gave me 6 times 10 to the minus 4. Okay, so that is actually this answer here. That is what we've got. 6 times 10 to the minus 4 is the same as 0.6 times 10 to the minus 3. So once we got to that point, okay, so then we would normally account for C, but actually, well, C's been halved, but what have we got to do to 6 times 10 to the minus 4 to get to 6 times 10 to the minus 4? Nothing. So C must not be having an effect. If you had to double it or halve it, sorry, if you had to halve it, then C would be first order. If you had to divide it by 4, then C would be second order. So yeah, another question, please. So yeah, that's it. Okay. So that's orders using data, So these are really common questions. If you, good, I'm glad you get it now. Okay. So these are really common questions. I've just been recording the 2019 papers. There's a really weird rates question in an AQA paper, and it looks really different to this, but actually it's just the same horse, different jockey. Okay. It's all about comparing others. Absolutely. So even when you've got 2 sets of data whereby you haven't got a fair test, you haven't got where the others stay constant and you want that one that changes. If you haven't got that information, if you know the orders of the others, you can take those into account first. And then once you've applied that, look at the difference in rate you've got on your calculator and the one that's actually in the table. Okay. Yeah, I've got a content guide. Absolutely. Yeah, it's crazy. Yeah, some of those questions are crazy, Jazz. Absolutely. Okay. So deducing orders from information, really, really important. Knowing what effect orders have on the rate is really, really important. So these are really common questions in the exam guide. I mean, the thing is, this is the same for all exam boards. Okay, this is absolutely the same for all exam boards. So, you know, it's the rate equation. So in the exam guide, you can look at the curated papers for other exam boards. There's a massive bank of questions in there in the exam guide for you guys, okay? And it does take a little bit of practice, Lyric. You're absolutely right. Okay, absolutely right. It does take practice. And there's plenty of those in there for you to practice on. And don't forget, every single question that's in that exam guide, there are 3 videos for it. Me basically planning what I'm going to do to answer the question, then me doing the question, and then me going through the mark scheme for it. Okay. Helen, we're not here to stress you out, okay? We're just here to make sure that you're in touch with your studies, all right? There's no pressure on anybody to do any of this. You know, all we're doing here at TT is just making sure that people are still ready, because if you get your result at the end of July and you're not happy with it and you want to appeal it, then you're going to be sitting an exam likely in September, which is 4 weeks after that. So it pays to stay in touch and be ready, especially when you, if you go into university to do anything where you're going to be using this information, because unis are likely going to assess you when you get there as well, bearing in mind that you haven't done any exams this year. Okay. Yes, if you do exams in September, that cannot affect your uni application process. Okay. Is there a question practice on this in the Exambulance? Well, I'll show you what we're giving to you for free at the end of this, okay? So you can check out a bit more. 2019 papers will be up very, very soon. Yeah, so it'll be in the summer, the timetable for the release of the 2019 papers. You know, we can't release the 2019 papers until the exam boards release them, okay? Until they're publicly available. So I'll take a sip, and who wants to do some Arrhenius? Give me a yay. Yes and no, Habiba. As far as the logistics, your guess is as good as mine. Time for Arrhenius. Let's go. All right, let's do this. So we're just going to have a review, okay? We're going to have a review. So Arrhenius equation, I want to explain it to you, all right? Because has anybody ever sat you down and said, right, this is what the Arrhenius equation is all about? Probably not, okay? So K equals A E minus EA over RT. So that is, let me zoom in on that, nice and big. So this is our Arrhenius equation, all right? K is obviously our rate constant. Minus EA, that's our activation energy, as we know what activation energy is. R is our universal gas constant, and T is temperature, okay, in Kelvin. So, Ronnie, don't you go hijacking my chat now with maths talk. Who'd have thought that we were heckling each other here at TT? Right. We know we were talking just about 20 minutes ago about how temperature can affect K. Looking at this, do we understand why temperature affects the rate constant K? Don't worry, Lyra, I'm going to go through it all. Yeah. Why? Because it's there. That's why. So in terms of calculating K, in terms of the Arrhenius equation, temperature's in there. So temperature is going to affect the value of K. That's how we know it's in the Arrhenius equation. Somebody asked me about catalysts before. This Arrhenius equation explains why catalysts affect the value of K. Why do catalysts affect the value of K, ladies and gentlemen? I'm going to wait for the answers. Agile, absolutely. Activation energy, Lyric, you got it. Because activation energy is in here as well. We know catalysts lower activation energy. So, of course, if it's in this equation, it's going to affect K, okay? R is a universal gas constant. That doesn't change, 8.314. That's it, like no change there. As to why it's in there, don't worry about it. This Arrhenius constant, does anybody know why that's in there? A. Okay, don't forget, this is not AE, it's just A times E to the power minus EA over RT. It always gets written as this, and they think it's the same thing, but it's not, okay? It's A times E minus EA RT. Good, it is a pre-exponential factor. Yes, it is a because it's the exponent. But what is it? Oh, jazz. Yeah, very closely. Very, very close. It basically accounts for, how can I put this? The number of molecules that have zero energy, okay? Or indeed infinite amount of energy, which is a really, 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 really tiny number, because not till you get to 0 Kelvin do you have particles with zero energy. And how can we possibly account for the number of particles that have an infinite amount of energy? So it's a really, really small number, okay? No, another, I like that. It's just another thing, you know, just don't worry about it. It's just in there, isn't it? You know, yeah, that's it, Raseb. Absolutely. Okay. So it accounts for the molecules that can't be accounted for in this molecule. We really don't need to worry about it too much. Okay. So I don't like this. I don't like this, you know, this format, if you like, of the Arrhenius equation. I much prefer this one. Okay. Which is taking the natural log of everything. So ln K equals minus EA over, let's make that a bit bigger, minus EA over RT plus ln A. Okay, this is a much kinder equation to have to rearrange. So whenever you're asked to find the activation energy or the temperature or anything like that, I would absolutely rearrange it. So all we're doing is taking the natural log of everything. Okay, so we take the natural log of K, then it has to be ln K. If we take the natural log of this, well, we're just canceling that exponential out, aren't we? Okay, so that's why that just stays as minus EA over RT. And then A, the natural log of that, is of course ln A. So what you can do is you can just rearrange this. If you're asked to find EA over RT, okay, what I would do is minus EA over RT. I'm going to tell you what, this is my simple brain and how my simple brain works things out. This is kind of like just like 10 equals, I don't know, 15, 8 plus 2. Okay. And that's the way I rearrange things sometimes. I just give them simple numbers. Well, if I want to find 8, what is that? Well, that's 10 minus 2. So minus EA over RT equals ln K minus ln A. Okay. And if you've got both of those values, then you can start working with this to find EA and so on and so forth. Okay. So this is not the one that gives you the straight line. This is not the one that gives you the straight line. Okay. We're going to talk about that in a second. But rearranging this Arrhenius equation, once you've taken the natural log of everything, should be more straightforward and a lot less scary. Okay, so there's two types of questions they can give you on the Arrhenius equation. I'm going to say it. I shit you not. There's only two ways in which they can ask you to use the Arrhenius equation. One is this: rearrange it, given all the other values, rearrange it to find K, or rearrange it to find the activation energy, or rearrange it to find the temperature. Okay, and you can do that. Okay, yeah, I used the naughty word, but rearranging it is nice and straightforward when you take that natural log. Don't try and do it with the exponential in there, because unless you're a much better mathematician than me, which is probably highly likely, let's be honest, because I'm a bit of a div, you know what? Why make it more difficult for yourself? It's like using skeletal formula in organic chemistry when you don't need to. It's like, well, hang on a minute, don't do that. Use a nice, simple displayed one. So that's what we're doing here, okay? So the minus lyric, don't worry about the minus. That just gets like, ignored, if you like. So if you're rearranging to find that, so let's say you got a value for ln K minus ln A. Let's say that's 100, okay? So what I would say is that minus EA over RT equals 100. So basically minus EA equals 100 times RT, okay? And then you end up with EA. But EA has to be a positive value. So as far as I'm concerned, as part of your calculations and stuff, and this is me just being like a crap mathematician and a bit of a cheat, I don't really care what sign comes out of that equation that we do, times in R times T. All I do is, in fact, this is more likely to be a negative number, to be honest with you. So you do end up with minus EA equals a minus number. So therefore EA equals a positive number. So EA has to be positive. EA, calculated EA, is always positive, 100%. Okay. Yeah, I'm sorry. The streaming is a little bit weird at the moment. I think like literally people using bandwidth because everyone's at home either watching Netflix or on TT. So there we go. So good. I'm glad that makes sense. I'm glad that makes sense. So that's our Arrhenius equation. Now so that's one way in which they can present the Arrhenius equation to you in an exam is just like give you that, okay, and then you just have to rearrange it to find a particular value. Done. Okay. Right, we're getting on to that. So what we can have is a different rearrangement. So we'll take this one in blue, okay, and we're going to rearrange it, okay, by doing this. I'm going to take this temperature out. I'm going to take it out of that equation, okay. I'm going to take it out of that equation. So what we end up with is for the graph, okay, we end up with ln K equals minus EA over R times 1 over T plus ln A. So you can see I've taken the temperature that was in there and I've just put it here. And I've done it as 1 over T because obviously it's coming from the bottom of that equation there. Okay, so it's times 1 over T. Yes. Okay, so I could say what we're doing is EA divided by T here, but instead of dividing EA by T, we're timesing it by 1 over T. It's the same thing. Okay, so this is just the rearrangement for the graph. Now, what this is, ladies and gentlemen, and I know you all know this, is y equals mx plus c. Okay, now that is a straight line graph, whichever way you look at it. Okay, it's a straight line graph. So is everyone okay with that? So what is the graph? Well, we've got this. Okay, so what are our axes here, ladies and gentlemen, on the graph? What's the X and Y axis? Corey, I've got a delay on this today. I don't know why there's such a delay. It's like 5 or 6 seconds. It's a bit crazy. Okay, good. So this is ln K, and this is 1 over T. Okay, so those are our axes there, because of course we've got Y is ln K, and X axis is 1 over T. So we do have a straight line. So this straight line looks something like this. All right. Now, what they might do is give you this graph and say, it can be either jazz. It doesn't matter. It doesn't matter, to be honest with you. So we got our straight line graph. All right. So first of all, EA over R, where does that come into it? How does EA over R minus EA over R come into this? Boom. Absolutely. It's the gradient. The gradient equals minus EA over R. Okay. Now, where the gradient comes into this, obviously, if you've got a graph with actual numbers on, you can find the gradient really, really easily. So given the graph, this is by far the easiest Arrhenius type of question where they give you the graph. So they give you the graph, or maybe you have to plot it for 3 marks or whatever waste of time they want to do in the exam with you. And you can find the gradient, literally dy by dx. Okay, so a difference in y over the difference in x, rise over run, whichever way you want to think about it. But you get a number. What is that number? Looking at this gradient, what can we say about the sign on that number? Good. It's going to be negative. All the way it's going to be negative. We are going to have a negative gradient. So the minus gradient, okay, which is a negative number, it is going to be a negative number. It always will be, okay? Minus gradient equals minus E over R. So what we can say, just for giggles, is just let's get rid of them. So essentially what we end up with, if we want the activation energy, that equals the gradient that you measure from the graph times our universal gas constant. And that's that. Okay. So all you need to remember is when you've got this graph, EA equals the gradient times our gas constant, and that's it. Okay, so the activation energy usually given in joules. So you might have to do a bit of jiggery pokery with kilojoules and joules to get your answer in the correct units that they want you to give your answer in. But it's all per mole. Okay, joules per mole. Okay, so that's all it is. Nice and straightforward. It's just calculating the gradient. Okay, so that's pretty much it. That's all they can do in this. Apart from, there's one other thing they can ask you. They could probably ask you, what's a value for A? What is A? How do we do this? How do we find a value for A? Boom, Isabel. Absolutely. So this here, whatever the scale is on this ln K, equals ln A. And of course, all we have to do to find A is basically E to the ln A, and A equals A. Okay, so we find the exponential of it. Okay, so you can find ln A, which is the intercept. And then, yeah, absolutely, Isabel, use E to find it from there. Okay, so that's it. So that's the Arrhenius equation. Like literally, guys, that's it. All right. So there is, yeah, see, never thought about that. And that's all it is. I'm going to stop sharing now because that's it in a nutshell. So that literally, I'm not even joking. That is everything you need to know about the Arrhenius equation in what? 15 minutes, 10 minutes, maybe. Okay. E is just exponential. Okay. So it's the button on your calculator, the E with a little square next to it. That's all it is. Okay. Boom. Awesome. I'm loving this. So there are only two types of question. Just to remind you, this type of question where they give you the equation and you need to rearrange it to find a value. Okay. And that just tests your mathematical skills. And then there's the graph. Okay. There's literally nothing else they can ask you about. Okay. Now in the content guide, obviously I've got videos explaining what the Arrhenius equation is, obviously in a little bit more detail than what I've just done with you now, for the equation and for the graph. Okay. Or you could just Google it. Okay. But you know what? Are you going to get a decent explanation? That's the question. That's the gamble you take. All right. Googling stuff, you know, sometimes you get really good information. Sometimes you get really crap information. So there we go. You do choose certain subjects. Yes, I'm confident that they will not make you sit all subject exams if there's just one that you want to appeal. So that's it. Okay. Can we talk about how E cell is directly proportional to ln K? Well, that's a different kettle of fish, isn't it? We'll be looking at electrode potentials. Don't worry, I promise you. Okay. So let me just show you really, really quickly what we've done for you this week. So what we're doing this week, obviously we're doing these live sessions. And I've just lost my window. Where has my window gone? I'm going to share my desktop one. Okay, so what you should see here is our schedule. Okay, so our schedule for this week. This is what we're doing here, the rate equation. So what I'll do tomorrow with you guys is we'll smash through some questions on the rate equation and the Arrhenius equation as well. So who's up for doing some questions? Yeah, a lot of people do lose marks in it. I don't know why. I don't think it's hard. It looks scary, but it's not hard. Anything in place for year 12s due to take exams next year? They've lost so much. Oh, have we done anything for year 12s? Oh, my lordy, we are doing exactly the same for year 12s and probably more for year 12s because we don't want to let them down. So 10 o'clock, 12 o'clock and 2 o'clock, biology, maths and chemistry every day. We're on YouTube doing this sort of thing with you for year 12s, 100%. And what we're doing is we're building up to an exam for year 12s in June. So you can we're going to coordinate everyone together to do an exam together and you get a grade and you can go back to your teachers and we'll give you like, I don't know, a certificate to say that we can vouch that you've completed all the content and you've got a certain grade in a mock exam. So that's what we're doing for year 12s. No worries, Lyric. Thank you very much. Okay, brilliant. So, great. We're going to do some questions tomorrow. Now, what we're doing as well is this, ladies and gentlemen. So, In here, I'm going to add some more. When you click the, oh, I should get rid of this actually. In here, so in the Exambulance, if you click the AQA content guide, OCR Ed Excel, it will take you to the content guide, whether you're a subscriber or not, all right? And what you'll see when you get there is some unlocked content. So for the next 24 hours, I have unlocked the content for rate equations, okay? Not all of them, all right? We've got very kind of dedicated and loyal subscribers. It wouldn't be fair to give everything away, but the key stuff to help you consolidate and make notes, you can access these. Okay, so I'll put little padlocks on these so you can actually see which ones are unlocked for you. Okay, but for now, I mean, you know, there's 3 or 4 in there that are unlocked for you, including the Arrhenius equation ones. If you want to go over that and make some notes, so you can see me going through orders of reaction. You can't comment. Okay, you can see the comments in there, but you can't comment. That is reserved for our subscribers. So for the next 24 hours, not only have I unlocked that content for you in the content guide, in the live class recordings, okay, in the A, I've unlocked the, where is it? The rate equation and Arrhenius equation one for you in there. So you can watch the live class that we did at the time when we were studying that earlier in the year. Okay, so that's what we're doing for you guys, just to kind of keep you in touch with your studies, help you out, and keep you motivated during these really uncertain times. Okay, so you've unlocked a new character. Yeah, it's kind of like that. Yeah, think of it, we can gamify this a little bit. Half-Life, Amy, yes, I know some of you have to do Half-Life, OCR, for example. So Half-Life, I haven't unlocked. Like I said, we can't unlock all the content. It really wouldn't be fair to our subscribers. If you want to see all the content, obviously you're going to have to subscribe. If you want to subscribe, that's absolutely fine. And if you're in year 1, get the year 1 content. If you're into year 2, get the year 2 content. Just do a month. Just to, literally, actually, if you subscribe for 1 month, okay, I reckon in 2 weeks you'd actually get all the content you need from the courses. It's that concise and that condensed, and I would like to say very well taught. Then you'd finish the content and smash it. Absolutely. What we've got in our schedule for you year 2s is we're going to do some papers with you. We're going to do some study with me, basically sit down with you, teach you through the TT study method and so on and so forth, and revision method, and just keep you ready, because who knows, all right? There aren't exams in the summer, but you could be that one of those people sitting an exam in September to improve your grade to get into the university you want to get to, okay? So exam practice on rates tomorrow. Absolutely. Okay. So we're going to be taking everything we've learned. Okay. And we're going to be applying it to some different questions. I'm going to pick some OCR, AQA, and Excel questions tomorrow. So yeah, we do. Oh, nerdy niffler. Stop it. Rate determining step tomorrow. You know what? Let's do a rate determining step question tomorrow. It's not going to take too long. We've run out of time today. Will you still get an A-level grade if you're going to take a gap year, not going to uni? Yeah, absolutely. You know, if you were due to sit your exams this year, you're going to get a grade. Oh, Ruhab, you're jumping on the bandwagon there. That's great. Okay. So live classes for subscribers, Esther, yes, we were always due. Now, subscribers, it's been a little bit mental, hasn't it? So we're just trying to do best by everybody right now. We were always scheduled a week off this week from our subscription live classes. Rich, Ronnie, and I are putting our heads together at the moment, thinking about what we can do, because the original plan was, let's revise. We've got exams in like 9 weeks time. We need to revise, get some exam technique in. We're going to get you guys polished and ready for your exams like never before. But of course, that's not going to happen now. So we're just having to rethink what we're doing with live classes. Of course, we are loyal to our subscribers. You know, we want to help all those people who have been left in the lurch with the cancellation of schools, colleges, and exams, and so on and so forth. We're just trying to do our bit for society, like everybody out there at the moment, just being helpful. But of course, for our subscribers, we go above and beyond, and we're just trying to figure out how best to do that for you guys. Okay, if you've got an idea for live classes, then drop us an email. Okay, just say, Rich asked me to send some ideas in. Email us through the website, or leave us a comment in the course or something like that. Let me know what ideas you've got for live classes for subscribers in the coming weeks and months, and we will obviously take them on board and do our best for you guys. Okay. Doing hard topics and stuff. Yeah, absolutely. Okay. So, no, you don't have to sit all 3 levels in September. If you want to, I would say if you want to basically appeal for your chemistry grade only, then likelihood is you would only sit your chemistry exams, but you would have to sit all 3 papers. They wouldn't just give you 1 paper. So yeah, but who knows? I mean, they may just kind of culminated in 1 massive paper for you. We just don't know. So, is it possible that those exams can get cancelled? Well, you know what? If COVID doesn't disappear, then yes, they're going to have to rethink those as well. So who knows? Who knows? We're literally taking each day as it comes right now, aren't we? Because of course, Boris basically shut us down yesterday, and rightly so. Okay, and rightly so. So let's all do our bit, and you know, stay in touch, guys, and look after yourselves. So if you wanted to sit them, would that be possible? Again, September is the time to be doing that. But who knows? We may still be in lockdown in September. We just don't know. We are in lockdown right now. Yeah, absolutely. Okay. If you haven't watched the announcement from last night from the Prime Minister, make sure you do. All right. So anyway, on that note, I'm going to go, guys. Okay. And I will see you guys tomorrow for some questions on rate determining step, Arrhenius, and orders of reaction and rate equation. And thank you very much for coming. Please, please, please spread the word. Give us a like. Okay. I've got 4 thumbs up right now, ladies and gentlemen. I think we can do better than that. All right. So hit the thumbs up for me. Make sure you've let everybody know that you've learned something today. And yeah, be good, be nice to one another, look after your neighbors and your family, and stay safe, guys. And I will see you tomorrow.